Welcome back to AI networking. This is the introduction to AI networking. We're going to continue this particular course over the AI enabled use case in networking. We're going to build two scenarios. The first one is we're going to build a network security with AI, and then the other one we're going to build a routing algorithm. So let's go ahead and get started. So let's go ahead and create a directory. Let's move into the directory of introduction to AI. We're going to make a directory for AI enabled use case. And we're going to call this in networking. Awesome. And then we're going to change to AI enabled. Sweet. So let's do a clear. Awesome. Remind us this. All right. Hope you guys can still see this. We're going to go ahead and create a touch file. We'll create an example file for this. And if we log in, see in our Explorer, we can see this. All right, sweet. So we can go ahead and get started with our code. We want to go ahead, we're going to use, the module we're going to use for this is we're going to use NumPy. We're also going to use our scikit-learn, but we're going to use a different model. We're going to use an isolated forest model, which uses the Gaussian distribution, other known as the bell curve. So we're going to use the isolated forest, which we're going to use to specify some suspicious traffic and normal traffic or accepted traffic. Then we're going to import the time module and then also the logging. All right, so let's get started. So we're going to import NumPy as NP. We're going to import time. We're going to also import logging. And then we're also going to pull in our machine learning module. Learn, and then we're going to use the symbol, and then we're going to import the isolated forest model. Awesome. So the first thing we want to do is we want to set our logging. So we're going to do a logging base config. We're going to set this for format. And we're going to put the format as %, and we're going to get the level name. Then we're going to import the message, and then that's an S as well. And then we're going to set the level to logging debug. Awesome. All right, so now that's set. Dealing with the bell curve, we need we need two parameters, but in this case we're going to actually set a size for our sample data. So what we're going to do is we're going to set our normal distribution variables. So we're going to set normal distribution variables. And then the first variable, we're going to set the mean, which will be 100. We're also going to set standard deviation. We're going to set that to 20. And then we're going to set our sample size to 1000. Awesome. Now we're going to set the the baseline traffic. So we need something to bash our model against. So we want to set a network traffic equals to numpy. We're going to do a random, and we're going to do a normal because we want to pull out some a bell curve, a Gaussian model. So we're going to do a mean, and then do the standard deviation, and then we'll pass in our size. Sweet. Now that's set, we want to go ahead and we want to set our instantiate our model. Instantiate model. In this case, we want to do model equals, do the isolated forest. And then what we want to do is we want to do a contamination, which is we want to specify what our anomaly is going to be. So we're going to put this set to 5%. So anything that falls in the bottom 5% or the top 5%, we want to flag that. All right. So now let's fit our model. And after this, I'll show you an example of what I mean. So we're going to do a fit. Let's fit our model. And we're going to do network traffic. So since this was a simple array, we're going to have to reshape it for a two-dimensional array. Awesome. All right. So now we instantiate our model. We want to go ahead and create a while loop. So we want to look at some traffic. So while true, this is going to be a continuous loop. So we're going to do, we're going to set new traffic. So new traffic. And just like our regular traffic, we're going to set a random dot normal. And then in this case, we're going to specify the same mean, the same standard deviation, and we're just, instead of the size, we're only going to put one size. So we just want one, capture one traffic flow. And then we're going to create a message. And in this case, we're going to do an F string. We're going to call this network activity. Detected. And then we're going to specify our new traffic. New traffic. And then this will be a single array. We want the first position, sorry. And now what we're going to do is we're going to get an anomaly score. So what we're going to do is, in this particular state, we're going to predict a certain anomaly with this new traffic flow, and then we're going to get a score, and it's going to be a 1 or a -1 to specify if it falls either in the anomaly or if it's not an anomaly. So we're going to do anomaly score. In this case, we're going to set the model, and then we're going to do a predict, and then we're going to pass in the new traffic. We have to reshape it because it's a single array, so we have to get this two-dimensional array. Awesome. So now we're going to do an if statement. So let's say if anomaly score equals -1, then we're going to log warning, and in this case we're going to do an F string, call this suspicious, and then we're going to pass in our message. Awesome. Now else, and then here, with that being said, you can also implement something, a response, say to mechanize, like blocking their IP address, or send alert, or anything that we want to do with that. But you can put that in this section. I just want to put that in the note so we know, kind of what to do with this. Instead of logging in, we can do something else after that. So we're going to do an else, and then we just want to log info. In this case, we just want to do another F string and just call this accepted, and then the message. Sweet. And then we want to sleep this. We want to simulate some pause between it. So just time, sleep, and we'll just do 1 second. Okay. All right, so let's go through this code again. So we passed in our packages, NumPy, the time module, the logging module. We put in our scikit-learn machine learning package. We're using the isolated forest, which is using the bell curve concept. So we set our logging, we set our standard deviations, our mean, or the size, sample size. Let's do 1,000. Let's get a lot more, so we can get a lot of data to bash this sample size with our predicted traffic. Here we setting new traffic. Here we're setting the flow, setting our methods, setting standard message format. Here we're getting from our prediction, we get an anomaly score. It's either going to be a 1 or a -1. Okay, and if it's a -1, we're going to flag it as suspicious, and if it doesn't, we're going to say accepted traffic. Awesome. Go ahead and save this, and then let's go ahead. Everything looks good. We should be able to run this. So let's go ahead and hit run. Anomaly score does not equal an array. Apologize. This is definitely an array. So we want to pull the first position. All right, let's clear that. So that should fix that. Let's go ahead and run. All right, so that's running. So let's go ahead and hit cancel. I'm gonna cancel this. All right, warning. Those should not have been warning. So where did we go wrong? So we did network traffic, new traffic standard deviation. We fit our model with the network traffic, the new traffic. We're passing it up. Should be new traffic. And then save. All right. So now let's go ahead and clear this. And let's go ahead, pull this up a little bit, and let's run it again. Okay, we got some accepted traffic. And then we have some suspicious traffic. That's 75, 60. Okay, so we got good enough data points on this. So let's go ahead and cancel this. Let's see here. So 9211, 75 was marked as suspicious. 66 marked 70. This one's also marked as suspicious. Info. Standard deviation 20. So let's look at this. So let's do some math on this. So if we right now I'm using this emulator that I'm using. I got this from NumWorks. So let's go ahead and plot this. So if we do a normal, we did 100, 125 at 95%. So anything that falls below 60 and 139 should be flagged. So there's something wrong with our code. So we have the size, standard deviation, 1,000. Got the size, we're isolating it. We're then fitting the traffic. Oh, let's see what's going on. We want this at 5%. We want this at a 5% status, right? We were setting it at 50. So that was the error right there. So we fixed that. So we do a clear. Let's try to run this again. We should be able to get this. Okay, now we have some more normal traffic flow. Okay, so anything that falls below 60, we should get a flag, and anything above 139, we should get a suspicious traffic. So while we're doing this, I want to kind of map out what this is saying. Let's get a little bit more context. So let's go ahead and have my remarkable tablet. I want to go share something, present my screen. Let's see here. I'm going to do accept it. And kind of what this represents is, this is showing is we have a line and we have our bell curve, all right, and our mean, which will be 100. And then we also have another line, all right, we specify on both sides. In this case, represents 60 and 139 or 140. So any traffic that falls between this bell curve is accepted. And anything outside of these thresholds, right, we'll call this, flag this as suspicious. So anything that's greater than 140, suspicious. Anything that's less than 60 or below will be flagged as suspicious. All right, awesome. So see what we got. So in this case, 137, this was pretty close. It flagged it as suspicious. This one's suspicious, this one's below. I did notice with running this machine learning, it's pretty close, but it's not all the way accurate. So this one's close to the threshold. It just flagged it as suspicious. All right, so let's go ahead and cancel this. See what we got. So we was getting a lot of septic traffic. And then right here, we started getting some suspicious. Let me look and see if there was anything that was under close to 60 or over 130, 140. And this one was close, but okay. Well, yeah, it looks like it's working, but I did notice that if it's fairly close between 1 or 2 points, it does flag it. Like I said, this is a machine learning model, so it's just learning. It's constantly adjusting. So yeah, this one's close, right on the cusp. But so yeah, that flagged it. Awesome. So with that being said, and let's go ahead and move to this next example. We'll go ahead and clean this up, terminate that. So what I want to do, so we want to move this. So let's create a new directory. I want to move this over and call this build. I'm going to call this network security. And then we're going to move the example here. And then what we want to do is I want to add a new folder here and call this one routing algorithm. All right. And then I'm going to just create the file in the Explorer. Let's make it more easier. py. Awesome. So now with this example, this one's a little bit more complex. I'm going to create a bunch of logging to help us understand this. So really, this concept is, or this particular script is more of going through the Dijkstra algorithm. It's pretty much just going to go over trying to set up a certain nodes, and we put some weight behind it between the distance between each node, and then it's going to, based off of, we have a start node and an end node, it's going to collect the shortest path, and it's going to output the shortest path for us. So we're going to import a new file. It's called heap, heap-q. If you're familiar with this is it's kind of like a module where you can accept a list, but what it does is it reorganizes it to the lowest value. So say if you had a list of 1, 2, 3, it's going to sort it to, or sorry, 1, 7, 3, it's going to resort it to 1, 3, 7. And we're going to leverage this because once we go through the while loop to determine the shortest distance, we need this to pop the newest or the shortest distance, so we can pop it to see if it's the shortest distance or not. But we'll explain all of that when I do the code. So we're going to do logging, import logging. And then let's go ahead and set our log. So we're going to do Let's do set logging basic configuration. And then let's be logging basic config. Let's set a format. We're going to implement $. Spread this out. This is quite lengthy. All right. So we're going to have the $. We're going to input the level name. We're going to set the message, and then we're going to do the line number because it's pretty lengthy, so we're definitely going to need the line number to help us follow us through this. So we need line number, and then we're going to do $, and then line number, and then D, and then we're going to set the level to logging debug. All right, so we'll get some more real estate so you can see this. I think you don't need to see that. Okay. So what we did was we're gonna on the login we're gonna have the level name, the message, and then we're gonna pull the line number so we know where the logging information is coming from. So you will see that. You see why I did this later. So let's do a class. We're gonna do a network graph. So we're gonna create a network graph class. So we're going to instantiate or initiate our dunder int, and we'll do a self, and then we're going to do a self graph. This is going to be a dictionary. The next function we're going to do add edge. And this is going to pass in a self. It's going to have in a node 1, node 2, and then the weight. And what this is we're going to, at the end, be able to add the edges, meaning the distance. So we're going to have a node 1, node 2, and then we're going to assign it a weight value. Okay. So we're going to do if node 1 not in self.graph, and then we're going to do self.graph, and we're going to add the node 1 equals an empty array. Right, and then we're going to do the same thing for node 2. Node 2 not in self-graph. And then we're going to do self-graph node 2 equals an empty array. And then what we're going to do is I'll do self.graph node 1, and then we're going to do .append, and then we're going to append the node 2, and then with the weight. And then we're going to do the same thing for graph node 2 append, And I'm going to do node 1 with weight. All right. Now we need one more function, and we're going to call this the Dijkstra. Dijkstra. Dijkstra self dot start node and end node. All right, so now this is where we're going to do our Dijkstra model to find the shortest path. So first thing we're going to do, we want to initialize the distance and visited directories. All right, so we're going to do a logging. No, actually, I want to do the distance first. I want to do the distance. And then in this case, we're going to set up a dictionary. So we're going to set node, and it's going to be a float. And we're going to pass in INF, which is, we're going to say not defined. And then for node in self.graph, all right? So now it's going to get all the nodes in the self.graph, and it's going to assign it this NIL float. And then we're going to log. We're going to do a logging, and we're going to do an info. And then we're going to do an F string, and we're going to say instantiate distance dictionary. All right, and then we're going to show our dictionary. So distance. All right, awesome. Now the next thing we need to do, we need to instantiate or set or initialize our visited dictionary. And this is going to be an empty dictionary. And then we're going to do a logging. It's going to be a lot of logging, guys. So logging, I'm going to do an F string. I'm going to do the same thing. Instantiate. I think I'll call it instantiating visited dictionary. And then what we're going to do is the same thing, and we'll call visited. Sweet. All right, next we're going to set the distance dictionary. So we're going to pull the start node. So we're going to get the start node. We're going to get that variable, and we're going to set it to 0. Okay, and then we're going to log that. So let's go to logging dot info, and then we're going to call this another F string called setting start node to distance. And then we're going to display distance. So we're going to display the whole dictionary each and every time we run this, so we can see as it get added. All right, so we did that. Now we need to set our priority our priority queue. And we're going to start this with a tuple, a list of tuples. So we're going to do 0, and then we're going to do start node. All right, so what this queue is going to do is going to track where we're starting at, and then as we add to the queue, we're going to remove it from the queue with this heap queue module. So we'll see that later. So let's go ahead and we want to log this. So logging, and we're going to do info, and then we want to do f string, and then we'll do setting priority queue, and then we're going to do colon, and then just call this priority queue. All right, now we want to go to the while loop, and then just do priority queue. So while the priority queue is not empty, we're going to loop through it. So first thing we want to do is we want to log, because at the top every loop I want to track what's the current queue. So we're going to do info, we'll do f string, we're going to do current priority queue, and we're going to specify the priority queue. So let's see what's the queue. All right, and now we want to use the first time we want to use our heap queue. So let's do current distance, and then current node, and then we're going to get this from our heap queue, and we're going to do the heap pop. So we're going to pop it. So soon as we set it, we're going to remove it. So that's what the pop is. So we're going to remove the priority queue. All right. So we're going to pop that, which is going to get the first one. It's going to pop the first one. So once it's sorted, it's going to pull the first one. In this case, since we already set this one, it's just going to pop this, and then you're going to, once we pop it and log it, you're going to see an empty array once we first do it. So now we're going to do a logging. We're going to do info, and do another f string. In this case, we want to, I don't know, I did message. Let's just do f string. We want to do called heap queue function. We'll call the function pop. Okay. The correct is heap pop. Let's call it the correct one. Heap queue pop. I believe that's heap pop. So we called that. I guess we should just call it pop. I think we know what it is. Let's just call it pop. Heap pop, and it's going to return values. The return values. So it's going to capture that. Return values. And we're going to do parentheses. We're going to pass in the current distance, and then we're going to get the current node. Okay. And then we're going to send, and then we want to show what the priority queue looks like after it's popped. Priority queue. Sweet. So once it's popped, we should no longer see the first position we get, so once we pop this first run, this will show an empty array. So we could do if current node in visited. So if it's in the visited, we want to log it, and then we want to say f string. We're going to do current node, and we're going to give this current node was found in visited dictionary. All right, and then we'll do a continue. So once it finds, it's going to exit out of the while loop. All right, so now we can do a visited, and then we're going to set current node. So we're at the current node, and we're going to set the value to true. So if we visit it, if we haven't, we want to say, hey, we want to add it, and then we want to log it, info, and then we're going to say f string added current node. Do current node to visited dictionary. All right, and now we're going to do another for loop. So now once we have it, we're going to pull all its neighbors. So we're going to do neighbors, and then wait, and then this will be the dictionary. So it'll be self.graph, and then whatever the current node is. So now we want to pull all of the neighbors that's currently in that we specified earlier in the add node. So it's going to append that in the list. So it's going to get all of the neighbors and the weights in that list, and do distance equals current distance plus weight. We're going to call this distant, because I think we called the dictionary distance. All right, so now we're going to log this, logging.info, and we're going to do an f string, and we're going to do neighbor, and then we're going to get the neighbor, actual neighbor letter, or the actual neighbor name. We're going to do distance calculations, and then we'll specify the actual math. So we'll do current distance plus weight equals, and then type in distance. All right. So after that, we need to check to see if the current distance is less than what's already in our distance dictionary. So we're going to say if distance is less than the distance of neighbor. So we're going to pull the neighbor. So if it's lower, all right. So if it is lower, so we want to say the distance dot neighbor equals distance. So now we're going to change it what it was before. So we're going to set it to the lowest distance. And then we're going to log this, logging info. And then we'll do another F string. And then we're going to do add neighbor. And specify the neighbor we're adding. To distance. In this case, this will be an update, so it's probably already added, but we can say neighbor to distance dictionary. And then we're going to supply the dictionary, the distance dictionary, so we can track what's been added. And then we're going to do a heap, and then we're going to do a push into a heap push. And we want to set the priority queue. And then we want to specify both the distance, which is the number, and then the neighbor. All right. So we're going to add that back to our heap. And then we're going to log, and then info. And then we'll do F string. We'll do called a heap queue. And then we'll call the function push with params. And we'll specify distance. And then we want to specify a neighbor. Then we want to look at the priority queue. So priority queue. And then priority queue. Awesome. All right. So once it gets added, we're going to add that back to our priority queue, so we can go through that the next neighbors and see and map out the next hop. Then we log that. So now what we need to do is pretty much, I think we're done. So we'll just need to do logging. And then what we're going to do is log the info. And then the F string, we want to say returned name distance. And then this will be the distance dictionary, and then end node. And then we just want to return distance end node. All right. So now, I know that was a lot. So let's go ahead and try to walk through just this part, just the graph. So we have it when we call or initiate the network graph. We're going to initiate an empty array in the graph. We're going to add the nodes, so that's pretty much self-explanatory. If it's not there, it's going to create an empty array. And if it is there, it's going to append both for node 2 the weight and node 1 and node 2 to each verse. So if node 1 and node 1 will get node 2's weight, it'll be assigned to it, and node 2 will get node 1 and then the weight. as we make sure I got that order right. Okay. And now as we go to the Dijkstra, this is just going to simulate creating the distance, instantiating a visit, making it easier. A visit dictionary makes so we know if we visited or not, so we can keep track of that. We're going to set the starting node to 0, which is the first run, and then once we add that, we're going to set the priority queue. I think let's call it priority queue. And so I have to do a change. Let's do Control F. I call this priority queue. All right, to make sure I don't priority queue, priority queue, priority queue. All right, sweet. I'm glad I'm going through this exercise. So we set the priority queue to, then we're going to get the current queue, and then once it loops, we're going to assign it, we're going to pop it, so we can get the current distance and the current node. And then with the current node, if we visit it, it's going to continue. It's going to continue and add it as true. We're going to log that. We're going to go through our neighbors. It's going to list all the neighbors. It's going to get the distance and the weight. And once it does that, it's going to log the neighbors with the distance, with the calculating with the current distance plus the weight, which is the distance. And then what we're going to do after that is if the distance is less than what's currently in that distance, if it is less than, we're going to add the new distance, and then we're going to push it to the priority queue with the new distance of the neighbor. We're going to log that, and then once we're done, it should log the returning distance with the end node. All right, sweet. So now let's go ahead and try to plot this. So now we need to create a network. So let's create network. I'm going to call this NetworkGraph. So we don't have to pass anything. And now what we're going to do is we want to create some edges. So let's do network, add edge. In this case, we're going to call this A. And then the other neighbor is B. And then we're going to give the weight as 2 for this one. We'll do a network, add edge. We got another one called A. And then we're going to do C. And we'll give that weight of 4. And then we're going to do network, add edge, another edge. And we're going to do B to C. I'm going to give this weight 1. And do a network dot add edge. And we're going to do another B to D. And we'll give this one 7. And then network dot edge. We're going to give C to D. And get this one 3. And network dot add edge to D to E. And give this one 1. All right, sweet. Now let's create some variables. Let's do start node. Let's create one that's called start node. We're going to give this A, and this do end node. Let's give this one E. And so let's create another variable called the shortest distance. And then we're gonna call network Dijkstra. And then we're gonna do start node. We're gonna do end node. And that should be it. And then we want to log it. So we're gonna do logging.info. A lot of logging. So let's do shortest distance from, I'm going to do start node to end node, and then we're going to give it the shortest distance. Sweet. So what we did to create our network, we instantiated our network graph, we plotted our network graph, we created a start node, an end node, we're calling our Dijkstra function, we're plotting both the start and end, and it should give us the shortest distance in the output. All right, so we'll go ahead and save that again, and let's cross our fingers and run it and see if it works. Sweet, we got some output. So let's go through this. It's a lot. So, which is fine, that's good. So that's why I'm here. All right, so the first thing we did, we instantiate the distance to the dictionary. If you notice, all of the A's, B, C, D, E, it all is not defined. And then we instantiate, I have to rename that. See an error typo right there, which is visited dictionary, which is an empty array. Start node distance. So the start node, which was A, right? So the start node is A, which it assigned A. So then it set the priority key, the priority queue for A. It's just the current. And then what it did was it popped A from the queue, which it gave us an empty priority queue. It added the current node A, which is visited. All right, so it added to the visit node. And then I thought I was supposed to display the visited node. So let me go ahead and clean up some data. Visited node. What line was that? Line 25. Visited node. Yeah, I want to display visited node. Let's do this. I want to display this because I want to know what's being displayed. All right, so let's go ahead and clear this and run this again. All right. And we want to start it visited. All right, so we're back here. So we popped. Now we added A to visit node. So this is the visited dictionary. All right, the neighbor was B. So we added 0. So 0 and then added 2. So it's creating the distance for that. So it added that. So now we got B into our dictionary. It's going to call, sorry, where are we at? We are at here, so it added that. So now we call the heap queue, we're pushing it, so we add it to the queue. So now we have the priority queue populated. And then we're going to go to C. C gets added with 4. And then we're going to push C to 4. So now we got 4C. So now the current priority queue, which is now it loops back over to the top of the loop. It's going to pop the first, which is B. It's going to visit B. It's going to say, hey, we're going to add that back in. And then it looks at its neighbors. It's connected to A and C. So it's going to pull A's is 4 and C is 3. It's going to go to C, add C into, originally it was 4, but now we're going to make C 3 because it's lower. So it got updated. So now we're going to push C to the priority queue, which is 3C, 4C, and then we'll go to D. It's going to calculate as 9. It's going to add D. It's going to have 9 into D. It's going to push D9 into our priority queue. It's going to then, the current queue will have 3C, 4C, 9D. It's going to pop 3C. All right, it's going to add visit it, so it's going to add C as being true. So then it's going to look at its neighbors, A, B, and D. 7, 4, 6. It didn't see A is currently 0, so it's not going to add that. And B is 2, so it's not going to add the 4. So then it's going to go to D. D is currently at 9. It sees it at 6, so now it's going to add it, change it to 6. We're going to push D6 into our priority queue, which it did that. And then now it's going to return the values of, so where we at? So it's popped. So now we're back at 3. So then it's going to pop 4C. It's going to say current C visited. So then it's going to skip that because it's already added. And then it's going to go to D, D6, and it's going to pop that. It's going to add D to the dictionary. We're almost done. So now we added D as it visited. It's going to look at its neighbors, B, C, and E. So it looks like B is too much, so it's not. It's at 13. Originally it's at 2, so it's going to skip over that. And C is 3, which is this current saying it's 9, so it's going to skip over that. So now it's going to add E because E wasn't defined. So we have E as 7, which is stated here. It gets added to the dictionary. And then we're going to push E7 to the priority queue. And then once we go to the priority queue, it's going to return. It's going to pop E7 because it was the lowest one in the queue. It's going to calculate D as its neighbor. It's going to have an 8, so it's not going to add that. And then it's going to look at D9. It's going to skip. It's going to pop that. It's going to skip over it because it's already visited. And then it's going to return the number 7. So then it's going to report the shortest distance to A. And A and E is 7. So I know that was a lot, but it was a good exercise that we went through that. So if we just do the math, so the path will be A. So let's go backward, D. So that'd be 1. D to C will be 3. And then C to, so it'll be A. So it'll be AC 4. So it'll be 4. C, and then 1. 0 is not counted. So AC4. So to E will be 7. So it'll be AC4 plus C to D. Oh, so it'll probably take, so it's A to B, which is 2, and then B to C is 1, which would be 3, and then C to D, which would be 6, and then D to 1 is 5. Okay, so it'll be A, B, B, C, C, D, D, E. So that would be the shortest path. All right, so like I said, this code will be on our Git repository. You're more welcome to download it, test it out. I can run another quick scenario just to double check. Let's do C and B. See what happens. Just a quick scenario, and B and C is 1. So there you have it. Once again, I know this was a lengthy video. This one took me a while to do, but I wanted to log all that so you guys and walk it through so you guys can understand kind of how routing protocols and algorithms work. And until next time.